Hey guys, it's your girl Jordyn from LearnCast, and today we're going to be talking about VSEPR theory. Now, VSEPR theory states that electron domains will try to stay as far away from each other as they possibly can because of electron repulsion. From this, we can visualize the different shapes that molecules make. Now, when I say electron domain, all that's really talking about is locations surrounding a central atom that have electrons, that contain electrons. Now, this could be a lone pair or it could be a single, double, triple bond, and each of these would be considered a single electron domain. Now, you need to know the difference between electron geometry and molecular geometry, because if you mix those two up, you're not going to be doing too hot on your test. Now, electron geometry, all it refers to is the number of electron domains around your central atom in your molecule. All you have to do is add up the electron domains surrounding your central atom, and for each of these numerical values, you'll have a name that's associated that you need to memorize. It's really easy, and I'll give you the breakdown. So when you have two electron domains, that's called a linear electron geometry. An example of this would be carbon dioxide, where you have your carbon central atom, which is double bonded to your two oxygen atoms, and each of those double bonds is considered one electron domain, and you add those up, you have two electron domains. With three electron domains, that's called trigonal planar electron geometry. An example of this is sulfur trioxide, where you have your sulfur central atom, which is double bonded to your three oxygen atoms. When you get to four electron geometries, that's called a tetrahedral electron. When you get to four electron domains, that's called a tetrahedral electron geometry. Now, you can use methane as an example of this, but water is also a very good example, where you have your oxygen central atom, which is single bonded to two hydrogen atoms. And we also know that oxygen has 6 valence electrons. So as a result, it will have two remaining electron lone pairs. It will have two lone pairs. And each of those lone pairs is considered one electron domain. So when you add up all of those bonds and lone pairs surrounding your central atom, you have 4 electron domains. Now, when we get into molecular geometry, that's talking about the shape of the actual molecule, which is rooted in our VSEPR theory. Now, I'll use water as an example. When you have the water molecule, your oxygen lone pairs, those two lone pairs will repel the two OH bonds, and this will cause the entire molecular structure to bend. As a result, this is called a bent molecular geometry. Now, I don't have time to tell you about all the different molecular geometries, but you can look it up. There's tons of charts online that are really helpful, and you need to memorize these. Now, skipping all the way to hybridization, I want to explain what hybridization is, because honestly, at first, I had no idea what it was. Now, hybridization is essentially when orbitals merge together to form hybrid orbitals. Now, you hear that and you're like, okay, great. But what does that even mean? So, when you have two atoms that are bonded together, you'll have your orbitals that overlap. And when those orbitals overlap, that's when hybridization occurs. Now, when we think about your sigma and pi bonds, which seems super intimidating, but they're not, your sigma bonds are the strongest covalent chemical bonds in which two atoms have head-on overlapping atomic orbitals. This could be between two s orbitals, an s and a p orbital, or two p orbitals. And if you draw a line between the two nuclei of the bonded atoms, that'll go straight through your sigma bond. Now, when we think about pi bonds are a little bit more complex. With pi bonds, your two orbital lobes are vertical, they're parallel to each other and they're vertical. And this causes electron interaction in that space, and that is your pi bond. Now, structurally speaking, when you think of your Lewis dot structure, sigma bonds are your single bonds, and pi bonds are your double and triple bonds. And each of these are separate. As an example, we can think about water, the water molecule, where we have two single bonds, and each of those would be sigma bonds. So you add those up and you'd say you have two sigma bonds in your water molecule. You can also look at propyne. Now with propyne, which has a empirical formula of C3H4, there are 5 single bonds and 1 triple bond. Now, each of those 5 single bonds would be accounted for in your sigma bonds. Your first bond in your triple bond would also be a sigma bond. Now you add those all up, you have 6 sigma bonds. The remaining 2 bonds in your triple bond would be considered pi bonds. So altogether in your propyne molecule, you have 6 sigma bonds and 2 pi bonds in total. Now, when we think about hybridization, it's super easy. You think about your electron configurations with your sp, d, and f orbitals. Now for Chem SL, you only really need to consider your s and p orbitals. And all it is you add up your superscripts from your little hybridization, which could be sp3, sp2, sp, and you add up your superscripts, and that should equal the number of electron domains surrounding your central atom. For example, if you have 4 electron domains surrounding your central atom, you'll have an sp3 hybridization. With S, you have your number 1 superscript, and your P, it's the 3 superscript. You add those together, you have 4, and that should be the number of your electron domains. And we can think about how much each of these orbitals carry from our previous units, where we know that the s orbital can carry 1 pair of electrons, the p orbital can carry 3 pairs of electrons, the d orbital can carry 5, and from this we know that if you just add up the superscripts, that's your essential hybridization coming from your electron geometry. Super easy. So today we learned about VSEPR theory, electron domains, molecular geometry, and hybridization. Thanks for joining me while we were learning about our VSEPR theory. Please follow us on Spotify, subscribe to our YouTube channel, check out our website, and stay up to date with our latest releases. Until next time, listen, learn, repeat.